Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So within this module, we are trying to understand that how does the operating system manage the hardware resource, that is the CPU, right? By providing this abstraction of a process. And within this second module, we are currently on the fourth topic, that is a process system called API. So within this topic, we are looking at the set of system calls that the Unix based operating systems offer, which allows us to perform different operations on the processes, right? So till now, in the previous few videos, we have talked about the process creation part. We have looked at the two system calls, that is fork and exec, and we saw how these two system calls together provide a mechanism which allows us to create and run new processes, right? So that was about process creation. Now we want to study about another important operation related to the processes, that is process termination, right? Just like there are system calls to create new processes, in the same way there are system calls. So basically there is the exit system call that allows us to terminate the process, right? So in this video we will look at the API of the exit system call, how does it work, right? And in which scenarios it is used. So without further ado, let's get started. So let us start the discussion with this slide. This diagram we saw in the very first video of this topic, where we described all the different operations on processes that we are interested in, right? So this is the like system call API for processes on Unix. So when we talk about the API consists of a bunch of system calls, and we are interested in the ones which are related to process management in Unix based operating system. So here are the different operations that we would like to be able to perform on processes. So that is process creation, process termination, waiting on other processes, and some other miscellaneous operations related to processes, right? So in the previous few videos, we have been talking about process creation, and we have seen how the two system calls, that is fork and exec, allow us to create new processes in the Unix based operating system, right? So if you are creating processes, then you definitely need a way to terminate those processes, right? And in the Unix based operating systems, the system call that we have for terminating processes is the exit system call. So now let us talk a bit more about termination of processes before we go on to look at the exit system call in more detail. So before looking at the exit system call, let us talk a bit about process termination, the different ways and scenarios in which the process can get terminated, right? So basically, there are two types of termination that I want to talk about. The first one is voluntary, and the second one is involuntary. So the difference between voluntary and involuntary is that in the first case, here the process is the one who is requesting the termination, basically initiating the termination. In this case, the termination is kind of voluntary, right? Whereas the second case, which we'll talk about, here the process does not request or initiate the termination. It is terminated by some external entity, right? Against, it's obviously, it is, since it is not the one who is requesting the termination, it is kind of forced termination, right? So it is involuntary in nature, right? So let us discuss some examples for both the different types of termination. So for the first case, that is voluntary termination, let's discuss the basic case when the process is exiting in a normal way, right? Any process has been assigned some kind of task, and when it completes that task, when the job has been done successfully, it will obviously terminate normally. This is the plain simple case. So for example, let's say you have copied a file from a source location to a destination location. For this copy operation, there will be a process, right? And once that copy is finished, then the copy process will terminate, right? That is like the job has been done successfully, so it is terminating. Another example is that let's say you are compiling a piece of code, right? So you give a source code as input to the compiler, and the compiler will then convert it into machine code and generate an executable. So if the compilation process is successful, if the conversion is successful, it will terminate in a normal way. So this is the plain easy case, the basic case. And in this case, the important thing is that the termination is voluntary in nature. It is requested by the process only, right? Another example is that when the process Another example of voluntary termination is that the process, let's say, encounters some kind of error, and since an error has occurred, it cannot cease to proceed, so it will terminate. So, for example, let's talk about the same copy operation, right? If you're copying from a source directory to, let's say, a destination directory which does not exist, right? Since the directory does not exist, the copy operation will fail, right? So in this case, the copy process has encountered an error, right? And that is why it will not proceed like with execution anymore. So this is another kind of basically here again the important point is that uh, even though there has been an error, right, the termination is voluntary. What is important is that even though an error was encountered, it is the process who is deciding to terminate. The copy operation failed, that is why the copy process is terminating. So let's take another example. Let's say the compiler process, right? So let's assume that the source code that you have given has some kind of programmatic error, syntax error. So the compiler during conversion discovers that error, and once it cannot proceed with compilation, it can decide to terminate. So again, the termination is voluntary in nature. So we discussed the two different cases, one that is successful or normal termination, and one where the process terminates when it encounters an error. But the common thing in both these cases is that the termination is voluntary in nature and initiated by the process itself, right? So this was about voluntary termination. Let's talk about another type of termination, that is involuntary. So the first case that I will discuss is that, let's say the process does something due to which an exception occurs in the system. So we have already talked about exceptions in the previous topic. So what is an exception? An exception is basically some kind of error or an unexpected event that is discovered by the CPU. And whenever the CPU detects such a error or an unexpected event, it immediately brings the operating system into the picture. The operating system has to deal with the error or the unexpected event. So this is an exception. And we talked about different reasons why exceptions could occur. Let's say the process does something illegal. Let's say it violates the privilege. So by privilege, I mean there is user mode and then there is kernel mode. And the process which is running in the user mode is not allowed to, let's say, access certain memory location, execute certain instructions which are reserved for the operating system, right? Another reason is that, let's say, there is some bug in the code. There is a division by zero, there is a stack overflow, or there is some kind of segmentation fault, right? So these are different reasons which basically can cause exceptions. So an exception, as I said, is an error or some kind of unexpected event that the CPU detects while executing the process. So let's say the process does something illegal or causes some kind of exception. So as we know, the CPU will bring the operating system into the picture, and the operating system will then take action. And very likely it is possible that the operating system will terminate the process. There could be some non-fatal exceptions where the operating system might deal with the exception and not terminate the process. Or there could also be the case where the exception handling code is incorporated in the process itself. So in that case, the process can be allowed to deal with the exception on its own. But let's discuss about the case when the exception is fatal. Let's say the process is trying to access a privileged memory location or trying to execute a privileged instruction. In this case, the operating system will terminate the process. And as you can see, this is involuntary in nature. It is not the process who decides to terminate. It will be killed, or we can say this is a forceful termination because the process has done something illegal. So the operating system can decide to terminate the process. And in this case, the process that is in concern, it is terminating in involuntary way, right? The final example that I will talk about is, let's say there is no such illegal exception in this case. There is a normal process, but let's say the user decides to terminate the process. In this case, the process will be killed by some external signal. So if you have when we use any graphical GUI based application like the word processor or the web browser, then the nature of these applications is that they will keep running as long as the user is using them, right? So there is no as such voluntary termination. Like the web browser will not close on its own, right? The Microsoft Word application will not close on its own. It's a GUI, it's an interactive application. It will run as long as the user keeps the window open, right? But when the user decides that they do not need that application anymore and they can click on the close button, in that case, this is a case where the process will be killed by an external signal, right? When the user initiates the termination, the user interface application will intercept that signal and then terminate the web browser or the word processor, any application that is in concern, right? So here again, the important thing is that the it is not the process which has initiated the termination, it is being killed by some external signal, right? So in both the cases that we discussed, in the first case the process does something illegal, causes some kind of fatal exception, and it is getting killed or terminated forcefully by some external entity, which is the operating system. And in the second example we discussed, in this case, the process is being terminated by some, let's say, initiated by the user, or it could also be killed by its parent process. Let's say it is no longer needed, right? So these are two examples of involuntary termination where the process is terminated by some external entity. It could be operating system, it could be some signal from other process, right? So these are the different ways in which processes can terminate, right? Different scenarios. So the common thing is that whatever is the way of termination, whatever is the nature of termination, the exit system call will eventually be called, right? So now that we have discussed a fair bit about process termination, let's look at the API of the exit system call. So now we will look at the interface of the exit system call, right? So this is how the exit system call looks like. So let's go over the different pieces. First of all, the very basic job of the exit system call is that it causes normal process termination, right? When the process requests the exit system call, it gets terminated in a normal way, right? Then it takes one parameter, one argument, that is an integer, and the argument is the status, which is the exit status. So what is this status? The status to be returned to the parent when it calls wait. So we'll discuss about this soon. But the idea is that when you are exiting, right, when you're let's say you're writing a code, and when you're exiting, you basically return a integer value, and that integer value can signify whether the operation was successful or was it error. If it was an error, then what kind of error was there. So exit code can be used to signify the status of the operation. For the general practice is that for success, the exit code is 0, right? In many times when you are writing the like C programs, you see at the end we write return 0, right? So what is that return 0? That 0 is signifying that if you're returning 0, which means that it is a common convention that 0 is for success, and if you're returning 0, which means that you have reached the end of execution, right? So if the return value of the entire code, if the exit code of the program is 0, then we can be sure that the code execution was successful. If it was not, then we can return any other kind of value, right? And that value, let's say 1, -1, whatever it is, can signify the type of error that has occurred. So that is the purpose of the status, right? And as you can see, this exit system call does not return any value, right? It is void. And first of all, there is this qualifier against the exit system call API in the man page, which says no return. The exit function does not return, because when the exit system call is executed, the process from which the exit system call was made, that process does not exist, right? It gets terminated. So where it will return to, right? So logically, it makes sense that the exit system call should not return, because there is no place to return to. So this was a basic description of the API. Let's now talk about some other points related to the exit system call. So now let us discuss the overall flow of the exit system call and some other points related to it, right? So as you can see, we have a process, right? Process A, and this is the code of the process. This is the main function, and somewhere in the main function, there is the call to the exit system call. One point is that it is not necessary to have the exit system call at the end of the code. You can call exit anywhere. Whenever you call exit, from after that, the execution will not happen. So let's say somewhere in the middle of the code, you encounter an error. At that point also, you can make the exit system call, right? So this is how the code looks like. Let's say the code is executing, and then we hit the exit system call. When that happens, the control will be transferred to the system call routine, the exit system call routine inside the operating system's code base, right? So any system call, basically it is some kind of routine in the operating system, and when we make a system call, the control is immediately transferred to that routine inside the operating system, right? So here, what we are passing to the exit system call is an integer value, which is signifying the status of exit, right? So as we discussed earlier also, if it is zero, then it is standard practice, agreed upon convention, that zero signifies that the process has exited in a successful way. The job it was doing was properly done. If the process returns some other value, then it can be used to signify some kind of error. But this is again just a agreed upon convention, not some kind of like that is something you have to follow. You can pass any integer value, right? Even if it is successful, you can pass some non-zero value, but then it won't make sense. So we have a agreed upon convention that if you're like exiting successfully, then you can pass zero. That is that will, in that way, other processes will have a way to know whether the process that is exiting was successful or not, right? So that was about the status value. So let's see what happens when we reach the system call routine inside the operating system. So the first thing is that this exit will cause normal process termination, and status denotes the reason. That is what we discussed. So as you can see, the process that invoked the system call, that is no longer there, right? So this was the process A, which invoked the exit system call, and after that you can see it has terminated. It is no longer there, right? And it has also passed the status value, which signifies how it exited, whether it was successful or it encountered some error, right? The second point is that exit frees up all the system resources allocated to the process, right? So basically, when the process would be executing, it would be using some kind of system resources like CPU, memory. Some memory would be allocated to the process. It might be reading or writing some files. It might be using some IO devices. So all of these resources will now be deallocated, and these freed up resources can be allocated to some other process. So the basic job of the exit system call is to terminate the process and free up the system resources. The next point is that exit does not return, it transfers control to the operating system, right? We saw in the API definition also that there was the no return qualifier. So this is something which is very obvious, is that when the process makes the exit system call, that will no longer exist. So there is no place to go, like return to, right? The process itself that invoked the exit system call is no longer there. So where will the process return to? So exit does not return, it immediately transfers control to the operating system, and that's it. There the operating system will terminate the process, free up the resources, right? So now let us see what happens next. We have passed this status value, right? This integer value. What will happen of this integer value? So we are not returning anywhere. So let's see how is that integer value, the exit code, processed. So what happens is that exit code is stored in the process control block, right? So this is the process control block from the x86 operating system that we have already talked about. So let me just recap about the process control block. So the process control block is a data structure that is used to represent a process in a system. It basically contains all of the information that is necessary to represent a process in the computer system, right? And for every process, there will be a process control block. It's just a data structure. It's a repository of all the information that is required to represent a process in the computer system. And here we have an example process control block, or PCB, from the x86 operating system. We have talked about this in previous videos also. So as you can see, within the process control block, there is a field that is int x state. So this is specific to the x86 operating system. There is a struct proc, right? This is per process state. This is the process control block. We are discussing this because this is easy to understand, right? And here there is a field x state which says that exit status to be returned to parents wait, right? So what is this parents wait? We'll talk about this. We'll also study about the wait system call in great detail in the next two videos, but just to give you overview of what will happen after exit, let's see this. So the integer status value that has been passed by the process which has invoked the exit system call, right? That is with the operating system. What the operating system does is that it takes that integer status, that exit code, and stores it in the process control block of that process. So although that process has terminated, the process control block is still there, right? This is a very important point. So let's see what does this mean. So the process has invoked the system call, it has been terminated, right? And exit does not return. And what happens next is that this is the process control block of that terminated process. That process, that running program is no longer there, but its data structure, its process control block is still with the operating system. It will also get deallocated, but only when the parent calls wait. So why is that? Basically, first of all, what will happen is that this exit status is important. It has to be returned to the parent, right? The parent had started this child process, right, through that fork and exec mechanism. So when the child process terminates, the parent would like to know about the exit code of the child process, like what happened with that execution, right? That is why. So what happens is that this status is stored in the process control block. We saw the field, right? We this x state field in this diagram you're seeing, this is the process control block, and let's assume that this is that field x state which stores the exit status, the exit code, right? So the point is that the PCB of the process which got terminated is not deallocated upon exit. It's used to store the exit status, right? Now that the process has terminated, but we still have the exit code in the process control block. So what's next? Next is that the parent process of the process which just got terminated, at some point in time, it will call the wait system call. So although we don't know about the wait system call, we'll talk about the wait system call in the next video. But in short, the wait system call is used to wait for wait for a particular child process to exit, right? So in this case, and it can be called post exit also, right? It can be called before the child process exits, or it can be called after also. So in this case, as you can see, after the child process has exited and it has passed the exit code, the exit code is stored in the PCB. Now when the parent process, that is process B, let's assume process A got terminated, let's assume process B is the parent of process A. So in process B, this wait system call will be invoked at some point in time. And what happens is that this in the wait system call, the argument to the wait system call is a pointer. In this pointer, which is a pointer to an integer, right? In this integer pointer, this exit status will be stored. So what happens is that the exit status is collected by the parent when it calls wait. PCB is also freed up. So what is happening here is that the parent has called wait and it has passed an integer pointer. So what the operating system will do, it will basically make this integer pointer point to this exit code, and then it will free up this process control block. And that is when we can say all of the memory, basically even the process control block of the process A does not exist, right? This is where all the state has been cleaned up only after the exit code has been returned to the parent process. So when the wait system call returns, so here you can see the exit code is now with the parent process. This exit code was passed by process A. Let's go back again, right? So in one of the previous slides, you can see when we invoked the exit system call from process A, this S, right, this was passed from here. It traveled to the exit system call routine. Then it got stored in the process control block of the process A. And finally, when process B, which is the parent process of process A, invokes wait system call, this exit code will then be transferred via the integer pointer to the parent process. So see how this exit code is traveling from the child to the operating system, then to the process control block, from there to the parent process. So the exit code has been propagated from the child process to the parent process. And in this way, the parent process can know what happened to the child process, and it can then take further action. If the child process was successful, then it might decide to do one thing. If the child process was unsuccessful, it failed, then it can do some other thing. So this is how multiple processes communicate and work together, right? Parent processes might have invoked the created those child process as subtask. If one subtask fails or if it succeeds, then the parent can decide to do some other subtask, right? So this is how the exit code plays an important role in the overall process management, right? So this is how you can see the wait system call also works. We will discuss about this in the next video in great detail. But the idea is that the exit system call, a few things that we discussed is that it will terminate the process, free up all its resources, will not return because from the exit because there is no place to return to. And finally, that exit code that has been passed, it will travel to the operating system. It will be stored in the process control block. That process control block will not be freed until the parent calls wait. When the parent calls wait system call, that process control block will be freed up and that exit code will be propagated to the parent process. And then the parent process can decide to take further action. So this is how the exit system call works in short, right? So now we'll see an example. We'll execute the exit system call and see some of the behaviors, right? So let's take a very short example and see the exit system call working. So here I have a piece of code, right, written in C, and there are just two printf statements and the exit system call. So the first printf statement says hello world, and the second one says bye world, and in between hello and bye we have a exit system call, right? So what do you think will happen? Which printf statements would be executed, right? So let's go and execute this piece of code. So here we have the terminal, and the piece of code is here, and I have already compiled this code. So let me execute this, and as you can see, hello world is printed, but we do not print bye world. Why this happens? Which is obvious, right? When we print hello world, after that we have a exit statement, and when that happens, the control will be transferred to the operating system, and after that we don't return. So this printf, that is the which is printing bye world, will never be executed. So that is why we only have one printf statement. So the point of this example is to show that the statements that follow the exit system call will not be executed. If all the code that is post exit system call, it will be obviously not executed, because once the exit is called, the control is to the given to the operating system, and the process itself is terminated, and the exit system call never returns. So this was the working of exit system call in brief. So the final thing that I want to talk about is that what if you don't call exit, right? When we write code, especially in the C language, it's not the case that every time we are calling the exit system call, still our process terminates, right? So why is our how is the code getting terminated even if we don't call the exit system call every time, right? Because the answer is in the C runtime, right? There is a explicit call to the exit system call associated. Basically, when you compile your source code, the C runtime gets bundled up into the executable, and when you run that executable, even if you don't call the exit system call explicitly, then there is an exit system call in the C runtime. So let's see the overall code flow and understand what happens. So for that, we will begin from process creation, right? So we will start with the exec system call. So this is where start a new program, right? So if you recall, the parent process calls fork system call, and that creates a new child process. But that child process is an identical one of the parent. To start a new program, we have to call the exec system call, right? So let's discuss the flow from the exec system call. So here we have a process A, right? So let's say it invokes the exec system call. And how does it behave? We have already talked about this in the previous videos. It passes the name of the file. So there are many varieties of the exec system call. The one we are discussing is the simpler one, right? You can pass a whole bunch of arguments to exec, but the simpler version of exec, you pass just the name of the file and the arguments that you want to provide to the new program that will be running. The new program that will run, the name is in this variable, that is file. So what happens next? What does the exec system call do? It searches for that binary that is being referred to by this file, right? And it loads up this binary and replaces the process which has just invoked the exec system call. So we have the same process, but it is now executing a different program, right? And it will take these arguments which were passed to the exec system call, and these arguments will be the input to this new program. So this was a brief recall of how the exec system call works, and we'll see how this is related to the exit system call. So this was the exec system call, right? And what happens is that the new program starts execution from main, right? After exec, we are assuming that the code starts from the main, that is the main function, right? So the flow looks something like this. We have a process and it executes this exec v system call, right? And then the control, basically once the new program starts, the control goes to the main function. But there is some part missing in this that we didn't talk about. The part is that before going to the main function, before jumping to the main function, what happens is that there is a startup function which is in the C runtime library, right? Which is the one that invokes the main function, right? In the startup library, as you can see, I have just kind of written a pseudo code. So what happens is that there is some platform specific startup code, right? Every platform, every different runtime will have different code. But what is important is that here in the startup code, there is the invocation of the main system call. And in the main you can see we are passing the argument count and the argv that we passed in the exec system call, that is being passed to the main function via the startup function. And you can also see this exit system call, right? This is the one which we are interested in, but I'm going through the overall flow. So the point that I want to make is that the when you make the exec system call, the new program is started from main, but that main, before that main runs, it is actually like called from the a startup function basically, which is in the C runtime library, right? So this is how the flow actually goes. You can see the main will be called, and here we are returning 0. What is this 0? This is the exit code, right? But we are not calling the exit system call explicitly. This 0 will be taken by the C library, and this status value, you can see int status is equals to main. Whatever the main function returns, that is stored in the status, and the C runtime library will call the exit system call. Now it is not necessary that this will be the flow. If you call the exit system call explicitly as we did in the code example, then this path will not be taken. But what I want to point here is that if you do not call the exit system call, which we do not do, which we normally do not do, we generally just return, right? We return whatever exit code that you return, that will be basically the return value of the main function will be used as a status code, and the C runtime library will ensure that the exit code, the exit system call is called with the appropriate code, right? So this is the part that I wanted to talk about, that if you don't call the exit system call, the C runtime library will do it for you, right? So what we will do now, we will now go through the flow in a different, in this visual way. Let's go through this code flow. This will help us to understand the overall flow of whatever we have discussed till now, right? We have discussed process creation. We talked about the fork, the exec, right? And the exit system call. Let us see all of that in one big picture, right? So let's say we have a process A, right? And it creates a new process. So it is, you can see it makes the fork system call. So this blue region is the user space. This red region is the kernel space. This is the convention we have been following in the previous videos also, right? This red arrow, red glowing arrow is actually a system call, and this blue arrow is return from system call. These blue arrows basically are signifying that we are executing code in the user space. So there are three actually access: process A, process B, and this is the C runtime, right? All of this blue region is in the user space, right? And this red arrow is where we are executing the kernel code. So let's say process A, it makes the fork system call, right? When it makes the fork system call, it will create process B. Let's assume that, and let's assume this dot represents that there is a context switch. We are switching from process A to process B, right? So process A made the system call, right? Here somewhere the new process B was created, and now we are switching. So when we return into process B. We entered from process A, but we returned into process B, right? This is how multiple processes execute in the operating system, right? We switch from one process to another. We'll talk about this switching in the next topic in more detail, but in short, we had one process, that is process A. After it called fork, right? Now there are two processes, and let's just assume that once the new process was created, the operating system decides that it wants to run process B, not process A, right? So let's go to process B, and now process B is an identical copy of process A, right? We have just invoked the fork. We have not yet called the exec system call. So let's say process B tries to run a different program. So it will make the exec system call. So when it makes the exec system call, the control will be transferred to the operating system. And when it returns, it will return in the C runtime library. This is where I'm trying to show how we will reach the main function. Before main function, after we have returned from the system call, we are in the C library, right? You can see this path after entering the operating system. When we make the exec system call, here we are kind of finding the program binary and replacing the binary of process B with the new program. And now when we are returning, we first go to the C library. We do not start executing the process B code directly, right? The path to the operating system and back always goes through the library, right? So in the library, there is this startup function, right? And we just saw in the startup function, there will be a whole bunch of setup things that the runtime library will do for you. But the main thing is that it will take the arguments that exec system call has passed, and it will call the main function with those arguments, right? That argv vector that you saw, right? That contains a list of arguments that have been passed to the exec system call by the process B when it before like making the exec system call. Those arguments will be passed by the startup function to the main, right? We saw this. And when the main function is done, it will again go back to the startup function. I'm assuming that we're not explicitly calling the exit system call from the process B's code. When that is not there, when you don't call the exit system call, the startup function will do it for you, right? So within the startup function, you can see whatever exit code was returned by main function. In that case, in our case, we saw we were returning return 0. So that 0 value is the return value of the main function, and that 0 is the exit code of that of this process B now. So the startup function will make the exit system call, right, and pass that 0 exit code to the operating system. So once this exit system call is made, the operating system will terminate process B, right? So process B is now done. And once that is done, it will, let's just assume that there are only two processes in the system. Process B is done. So once process B is done, the operating system will then return to process A. So this is how all of the different system calls work together. You can see there is fork, there is exec, and there is exit. We have created a process, started a new program, we have terminated the process, and you can see how the overall flow looks like, right? And in process A, we can call the wait system call to collect the exit code that is still lying in the process control block of process B. That part I have not shown, but that will also happen, right? So guys, this was it for this video. In this video, we discussed about process termination, the different scenarios, the different ways in which processes can get terminated. We talked about the API of the exit system call. We saw one example. And finally, we also talked about what happens if we do not call the exit system call, which we normally do not do. So we saw that in the C runtime library, there is an explicit call to the exit system call. And we also understood what is the significance of return 0. Right? What is that return 0 statement? That return 0 is passing the 0 as the exit code to the C runtime library, which will then invoke the exit system call that will terminate the process for us, right? So guys, this was all about exit system call. This was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.